In section 7.7, we look at complex numbers. And I'm going to start with a couple of definitions. Up until this point in the class, we have gone with the assumption that we cannot take the square root of a negative number because there is no real number that can be a square root of a negative. Well, in this section, we're going to define a new number that we call I to be the square root of -1. And if I is the square root of -1, then that would mean that I squared would be -1. Again, because that's the definition of a square root. So this number I is a number that you can square to get a negative. And because you're squaring a number and getting a negative, this number can't be a real number. And that is why we actually call it I, because I is what we call the imaginary root. Now, along with this, let me remind you of one of our rules of radicals, which says the square root of A times the square root of B is equal to the square root of A times B. There's actually a little bit more that goes with this rule that we didn't talk about because we didn't need it up to this point. But this rule is only true if either A is positive or B is positive. They can't both be negative is what that means. So one or the other or both have to be positive for that to be true. So this definition, along with this rule, allows us to simplify some radicals that we were unable to simplify in the past. So, for example, if you just look at the square root of -36, up until now we would say this is not a real number. However, we can now rewrite this as the square root of 36 times the square root of -1. And again, this is using the rule here. We know that -36 is 36 times -1, and the rule says that we can break this apart as long as one of these two numbers is a positive number, which we have satisfied. Now we can simplify this further because we know the square root of 36 is 6, and we know the square root of -1 is actually I. And so this simplifies to 6I. For our next example, we have the square root of -20. Now, this is a little bit different when it comes to simplifying the square root of -20. First of all, let's do this. Let's think of -20 as the product of 20 times -1. And we know the square root of -1 is I. And so this is the square root of 20 times I. And we would normally put that I in front of the radical. So we can write this as I times the square root of 20. However, we know the square root of 20 can be simplified as well. Particularly, we could say 20 can be broken down into 4 times 5. And we know the square root of 4 is 2. And so we have I times 2. That is 2I, and then radical 5. And this is the typical way that we would write this answer. For our next problem, we have negative square root of -9. What's important here is that you do not cancel these negatives. So be careful to not cancel those out. Instead, you have to follow the same procedure that we've been following. So I'm going to express -9 as 9 times -1, and notice that we are keeping the negative that was on the outside of the radical. It's still there. Now, simplifying, we have a negative sign. We know the square root of 9 is 3, and we know the square root of -1 is I. And so this is the square root of negative 3i. In our next example, we have radical negative 17. So again, it's just like the last one. But what I want you to get to notice here is that in each of the previous three problems, when you have a square root of a negative, the negative can simply come out of the radical. And when it comes out of the radical, it turns into an I. So that is a shortcut that you can take here. So we're going to pull the negative out of the radical here. But when we do this, it becomes an I. And so this becomes I times the square root of 17, and that is our final answer because radical 17 does not simplify. Now for the next problem, this is a relatively straightforward example. What we need to do with the square root of negative 4 and the square root of negative 9 is simplify each one of those. And so if I follow the shortcut that we had from our last example, the square root of negative 4 would be I radical 4, and the square root of negative 9 would be I radical 9. And if you simplify this further, this becomes 2i times 3i. And 2i times 3i is 6i squared. But this is not our final answer because, as we defined in the beginning, I squared equals negative 1. And so this is literally 6 times negative 1, which simplifies to negative 6. Now, what's worth noting here is that you cannot do this problem another way. And I want to point this out. And I'm going to make this very clear. I'm going to say this box says, do not do this. So let's say we have our last problem, square root of negative 4 times the square root of negative 9. It is tempting to say that this is the square root of negative 4 times negative 9, which would simply be the square root of positive 36, which we know is 6. Well, what's wrong with this? Well, we have the same problem, right? This problem here and this problem here are the same, but I'm getting two different answers. I get one answer if I do it this way. I get a different answer if I do it a different way. In mathematics, this is unacceptable. So we made a mistake here in the second method. You can't do this because what you're doing is you're multiplying these radicals together even though both numbers are negative. And this is precisely why back here in our rule, it says that you can only multiply these numbers together if either A or B is positive. They cannot be two negative numbers. So I just caution you with this. Make sure that you don't do this. Make sure that you instead simplify each of these radicals separately and then get your final answer. Okay, moving on now, we're going to talk about complex numbers. All of the numbers that we dealt with on the previous page were what we call imaginary numbers. Anytime you have a number times I, that is an imaginary number. So what are complex numbers? I'm sure many of you have heard of complex numbers and imaginary numbers before, and so you might think they're the same thing. They're related to each other, but they are not the same thing. So here's a definition of complex numbers. If the numbers A and B are real numbers, then A plus B times I is what we call a complex number. So a complex number is complicated. It's a real number A plus another real number B times I. And the real number A is what we call the real part of the complex number. And the real number B, which is being multiplied to I, we call that the imaginary part of the complex number. So let's just look at a few examples of complex numbers. A number like 2 plus 3i is a complex number. The real part of this complex number is 2, and the imaginary part of this complex number is 3. Not 3i, just 3. Another example of a complex number might be something like this. Negative 1/2 plus radical 3 over 2 times I. Now, this is not as nice a complex number. It's pretty complicated, but it satisfies the same conditions. The real part of this complex number is negative 1/2, and the imaginary part is radical 3 over 2. So complex numbers can have real and imaginary parts that are positive, negative, fractions, decimals, etc. So for example, 5.6 minus 4.3 times I is a complex number. The real part is 5.6, and the imaginary part is negative 4.3. Now, all complex numbers can be written in this so-called standard form. And the standard form of a complex number is A plus B times I. So let me just remind you that if you have a number like 5, we know 5 is a real number. But because you can think of 5 as 5 plus 0 times I, 5 is also a complex number because it can be written in this standard form. The real part of this complex number is 5, and the imaginary part is 0. And anytime the imaginary part is 0, this number is always going to be a real number. But my point here is that all real numbers are also complex numbers. All real numbers can be written in the form A plus B times I. It's just that when you have a real number, the imaginary part is always going to be 0. Now, also, you can take a number like 3i, which is what we call an imaginary number, but it's also a complex number because we can think of 3i as 0 plus 3i. In this case, the real part is 0, and the imaginary part is 3. And this number is what we would call an imaginary number. But as I just mentioned, all imaginary numbers are also complex numbers. So every single number that you see listed here, these are all complex numbers. These two numbers here, these two situations, are special situations. If either the imaginary part is 0 or the real part is 0, you either have a real number or you have an imaginary number. Okay? So again, all of these are examples of complex numbers. So let me just recap. Negative 7i is an imaginary number. It's also a complex number. However, 3 plus 4i is a complex number, but not an imaginary number. So again, to be an imaginary number, the real part has to be 0. Here, the real part is 3, not 0. So I make a bigger deal about this than I probably should, but what I want you to come away from this little discussion is a notion of what it means to be a complex number. And also with that, I want you to know that imaginary numbers and complex numbers are related, but they are not exactly the same thing. Okay, so next up, what we want to do is talk about basic operations with complex numbers. So we should be able to do things like add, subtract, multiply, and divide. And this is a really simple process. When you add two complex numbers together, you are going to add the real parts together, and you are going to add the imaginary parts together. Now, you don't have to show your work here, but if you want, you can remove the parentheses. And then essentially all you're doing here is you're combining like terms. And so if we combine like terms here, 3 plus 2 is 5, and 5i minus 7i is negative 2i. For our second example, we're subtracting two complex numbers. Now, subtraction works just like addition, except that you have to distribute the negative sign. And so this is 3 plus 5i minus 2, and then minus negative 7i becomes plus 7i. And then once again, we just need to combine like terms. So 3 minus 2 is 1, and 5i plus 7i is 12i. Next up, we'll look at multiplication. So in example 3 here, we have a real number, 5, multiplied to a complex number, 3 minus 4i. And the thing to do here is distribute. And we know that 5 times 3 is 15. And 5 times negative 4i is negative 20i. Okay, so adding, subtracting, and multiplying complex numbers, at least so far, is a relatively straightforward procedure. Now in our next example, it's the same type of problem, except now we have an imaginary number multiplied to a complex number. Once again, we need to distribute. 4i times 3 is 12i. And then 4i times negative 5i is negative 20i squared. Now, this answer is correct, but it's not simplified. Remember, we should never have I squared in our answer, because I squared from the beginning definition we know is negative 1. And so this is really 12i minus 20 times negative 1, which is 12i plus 20. And then one last thing, when you write a complex number in standard form, the real part should go first, and the imaginary part needs to go second. So this is our final answer here. In our next example, we are now multiplying two complex numbers together. The process for multiplying two complex numbers is the FOIL procedure. So we're going to multiply 5 times 4, 5 times negative 3i, 2i times 4, and 2i times negative 3i. And if we do those multiplications, we end up getting 20 minus 15i plus 8i minus 6i squared. So the last thing we need to do now is simplify our answer. Well, negative 15i and positive 8i combine together to give us negative 7i. And then remember, I squared is negative 1. And so instead of writing negative 6i squared, that's negative 6 times negative 1. And this can be simplified to 20 minus 7i plus 6. And finally, we can add 20 and 6 together to get 26 minus 7i. Now our next problem is pretty much just like the last one, except that we have 3 plus 2i quantity squared. What you want to make sure you don't do here is don't distribute the square to each one of these. That is incorrect. Instead, what we need to do is use the definition for squaring and write out the factor twice. And then from there, we'll go ahead and do our normal FOIL procedure. And if we do that multiplication, we get 9 plus 6i plus 6i again plus 4i squared. And then simplify. 6i plus 6i is 12i, and 4 times I squared is 4 times negative 1 because I squared is negative 1. And this gives us 9 plus 12i minus 4, which simplifies to a final answer of 5 plus 12i. And for our final example on this page, we have a very special type of multiplication. And we'll do this multiplication in just a minute, but let me talk a little bit about these two numbers here. 5 plus 3i and 5 minus 3i are what we call a conjugate pair of complex numbers. Conjugate pairs are two complex numbers that have the same real part but opposite imaginary parts. So same real part but opposite imaginary parts. And that's what you see here. Both of these complex numbers have a real part of 5, and the imaginary parts are positive 3 and negative 3. Now, conjugate pairs of complex numbers are special because when you multiply them, you get a very special product. So let's go ahead and go through and FOIL and see what we get. So 5 times 5 is 25. 5 times negative 3i is negative 15i. Positive 3i times 5 is positive 15i. And 3i times negative 3i is negative 9i squared. So one thing you should notice is that when we go to simplify this, these two middle numbers, negative 15i and positive 15i, are going to cancel out. Also, you know that I squared is negative 1. So this becomes 25 minus 9 times negative 1. And that simplifies to 25 plus 9. And 25 plus 9 is 34. And so the bottom line here is that conjugate pairs of complex numbers are special because when you multiply them together, you will always end up with a positive real number. So let's write that down. Conjugate pairs of complex numbers have a product that is always equal to a positive real number. So what it means is your answer is not going to have I in it. That's what it means to be a real number. And it will also be positive. Let me show you one more little detail with this whole topic here. In general, if I have a complex number a plus bi, its conjugate is simply a minus bi. And if you take the product using FOIL, you get a squared minus abi plus abi minus b squared I squared. And you can see that even when we do this in general, these middle terms always cancel out. And you end up with a squared minus b squared I squared. Now let's think about this. I squared, we know, is equal to negative 1. So anytime you multiply something by I squared, that negative 1 is always going to end up changing that sign. So in this case, it becomes positive b squared. So the product of two complex numbers that are conjugate pairs always ends up being a squared plus b squared. And this is a shortcut. This is a faster way to take the product of two complex conjugates. So, one more little tidbit about this. What this means is that if I wanted to multiply the complex numbers that we have up here, I can do this the quick and easy way by taking the real part, which is 5, squaring it, taking the imaginary part, which is 3, squaring it, and then adding those together. And this is 25 plus 9, which is 34. Right? Same answer that we got before. So, complex conjugate pairs are really important. So let's do one more. In the next example, we would like to multiply the complex number negative 2 plus 3i by its conjugate. So that means we're going to take the number negative 2 plus 3i and we're going to multiply it by, well, what's the conjugate? It's negative 2 minus 3i. And if you want, you can go through and you can FOIL, draw the arrows, do the work. I'm going to use the shortcut. The shortcut to multiplying a complex number by its conjugate is to take the real part and square it, plus take the imaginary part and square it. And this gives us, in our case, 4 plus 9, which is 13. Quick and easy. Okay, for our next example, we're going to look at division of complex numbers. So how do we divide the number 5 by the number 4 plus I? Well, it turns out we don't actually do the division. What we do is we use a trick. We use a shortcut. What we're going to do is take this fraction and we're going to multiply the top and the bottom by the conjugate of the denominator. So the conjugate of 4 plus I is 4 minus I. And you have to multiply by the same thing to the top and to the bottom. And so this is 5 times 4 minus I over 4 plus I times 4 minus I. Now, if we just do that multiplication, on the top, I'm going to leave it the way that it is. You could multiply it out if you want, but I'm going to leave it. And then in the bottom, we're going to have the product of two complex conjugates. And again, we can do the shortcut here. This is just 4 squared plus. Now, what is the imaginary part here? The imaginary part is the number in front of I. And the number in front of I here is 1. And so it's going to be 4 squared plus 1 squared, which is 16 plus 1, which is 17. And then on top, we can multiply this out, which gives us 20 minus 5i. Now, your final answer should be a complex number. So what we do next is we just separate this into two parts. So we take 20, divide it by 17, and then we take negative 5 and divide it by 17. And there's our answer. And for our final example on this page, we have another division problem. We would like to divide the complex number 5 minus 7i by the complex number 3 plus 4i. Of course, you don't really do division. Instead, we're going to multiply the numerator and the denominator by the conjugate of the denominator, which is 3 minus 4i. And then from there, we're going to multiply it out. So the denominator is relatively straightforward. We have a complex number multiplied by its conjugate. So we can use the shortcut, which is real part squared plus imaginary part squared. And now for the numerator, you need to make sure you go through the entire FOIL procedure. And so 5 times 3 is 15. 5 times negative 4i is negative 20i. Negative 7i times 3 is negative 21i. And finally, negative 7i times negative 4i is positive 28i squared. Now, we still have a lot of simplifying to do, but this is going to turn into 15 minus 41i, and then plus 28i squared becomes negative 28, because remember, I squared is negative 1. And then in the denominator, we have 9 plus 16. Simplify a little further. On the top, 15 minus 28 is negative 13, minus 41i, and 25 in the denominator. And then finally, we separate to write our answer in standard form. Let me clean that up a little bit. And so our final answer is negative 13/25 minus 41/25 times I. And for our last topic with complex numbers, we are going to look at powers of I. So this would be whole number powers of the imaginary root I. We already know that I to the first power is I, and we know I to the second power is negative 1. The question is, what is I to the third power? Well, it turns out that I to the third power is negative I. Now, I'll show you why. I to the third power is the same as I to the second power times I to the first power, using properties of exponents. But I to the second power is negative 1, and I to the first power is I. And negative 1 times I is negative I. So that is why I to the third power is negative I. What about I to the fourth power? Well, again, here it turns out that I to the fourth power is 1. And the reason why is because I to the fourth power can be thought of as I to the second power times I to the second power, which is negative 1 times negative 1, which is positive 1. Well, it turns out that after this, it begins to repeat. Let me just show you why. I to the fifth power can be thought of as I to the fourth power times I to the first power. But we now know that I to the fourth power is 1, and I to the first power is I, and 1 times I is I. And so if I do I to the fifth power, we're going to start over again in this pattern of results. And it keeps on going. So I to the sixth power is negative 1, I to the seventh power is negative I to the eighth power is 1. I to the ninth power is I to the 10th power is negative 1, I to the 11th power is negative I, and I to the 12th power is 1, etc. So it goes on forever. And so if I tell you something like, what is I to the 373 power, you should be able to figure this out because you know that it's going to go through this pattern. So one way to do it, which would be kind of silly, would just be to count your way to 373. And so that would look something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, etc., right? And then wherever you stop, when you get to 373, one of those values would be your answer. Okay, well that's kind of silly to do it that way. It's time consuming. So another way to do it is to observe that every time you go through the pattern completely, you go through 4. So the pattern repeats as a group of 4. So the first question is, how many groups of 4 are there in 373? And to answer that question, we can simply take the exponent 373 and divide it by 4. 4 goes into 37 9 times. 4 goes into 13 3 times. And what you have there is 373 has 93 groups of 4 with a remainder of 1. Well, the 93 groups of 4, what that means is that if you were to count your way to 373, you would go through the pattern of 4 93 times. We aren't interested in that number. What we're interested in is how many are left over. So when you go through the pattern 93 times and you have 1 left over, that means you're going to end at I to the 1. And so literally, this power, I to the 373, is the same as I to the remainder when you divide by 4. And in this case, that's I to the 1, which is I. And this always works, no matter what the power is. Let me just show you one more. Suppose we wanted I to the 42. The simple process is, you take the power 42, you divide it by 4. 4 goes into 4 one time. 1 times 4 is 4. subtract, bring down the 2. Four goes into 2 0 times, and that is your remainder. So we know that 4 goes into 42 10 times with a remainder of 2. This means that I to the 42 is the same as I to the 2. Again, it's all about the remainder. And you know I squared is -1. So when doing these, the only thing you have to memorize is the first block. And that's just kind of a cool thing about powers of I. Okay, so that concludes complex numbers.